Welcome, everybody. Welcome to everybody who's joining us for Class 7 of the Digital Data Flows series, hosted by Future Privacy Forum and Brussels Privacy Hub at the University of Free Brussels. We're really excited to have you guys all here this morning or this afternoon, depending on where you're joining us from. This is one of the first time that we've conducted these classes 100% remote, so we're really excited that people are joining, and we're looking forward to having a really robust discussion using the remote technology. And we are recording this session. My name is Stacy Gray. I'm going to do some introductions and hand it off to our excellent speakers today. First, a little bit about Future of Privacy Forum. We are a nonprofit research think tank based in Washington, D.C. in the United States, but we also have an increasingly global presence, including an office in Brussels and an office in Seattle, Washington. Our mission is to bridge the gaps between industry, privacy advocates, academics, and policymakers in government who are working on these very challenging issues involving data privacy. And we do a lot of work developing privacy protections, ethical norms, codes of conduct, and standards across many different work streams of consumer privacy, from location data, ad tech, to smart cities technology and Internet of Things. And of course, the topic that we're going to be talking about today, which is mobility and autonomous vehicles and connected cars. Last year, we launched this series, which is called the Digital Data Flows series, in collaboration with the University of Free Brussels, specifically the Brussels Privacy Hub, in order to specifically fulfill the mission of bringing more information out there about data flows and technology to policymakers who are interested in it from a privacy perspective. So through that lens, we are not going to be talking today specifically about law. We're not going to be telling you which policies we think are the best or which policies are necessarily even out there, although I'm sure we're going to touch on a little bit of that. That is for policymakers. Our mission today is to bring you the information that you need to consider those issues for those who are interested in this topic. So this is the 7th in a series. We are offering a certificate to those who complete the series. So if you're interested in that, let us know via the registration form or send us an email. You don't have to have attended all of them in person. They can be watched remotely. And if you're interested in that, or if you're just interested in the topics, you can find all of the archived videos and slides from our previous classes at fpf.org/classes. So on to our speakers. This is very exciting. One of the speakers today is my colleague, Chelsea Colbert. Chelsea, prior to joining FPF, was an associate at an international business law firm in Canada and was a privacy and data governance counsel to Sidewalk Labs. She holds a JD with a major in technology, law, and policy from the University of Ottawa. And currently, Chelsea is a policy counsel here at the Future of Privacy Forum, where she leads FPF's portfolio on mobility and location data, which includes connected cars, autonomous vehicles, ride sharing, micromobility, drones, robotics, and data sharing related to all of those fields. So very exciting that Chelsea's going to be leading a lot of the discussion today. We are also joined by Professor Bryant Walker-Smith. Bryant is an associate professor of law and engineering at the University of South Carolina here in the US. One thing that's exciting is that Bryant is trained as both a lawyer and an engineer. And so Professor Smith advises startups, nonprofits, governments, including the United Nations, on emerging transportation technologies. He co-authored the globally influential Levels of Driving Automation and drafted a model law for autonomous driving here with the Uniform Law Commission, which some of you may be familiar with, and taught some of the first legal courses dedicated to automated driving. Back in 2012 on automated driving, hyperloops, and flying taxis. So he has affiliations with the University of South Carolina, the University of Michigan, and Stanford University, and you can find his publications at newlypossible.org. So today, just now that people have had a chance to join, just a couple of logistics about how we're running the class today. We're going to have 3 sessions of about half an hour each, and we're going to stop for question and answer at the end of each of those sessions. So there will be 3 opportunities throughout the 2 hours of class for you to engage and ask questions, and we'll have a little bit of discussion. The best way to do that is to use the Q&A feature in Zoom, where we will be monitoring. You can submit questions anonymously, you can upvote questions, and that is the best way to do it. If you put things into the chat, we might see it, but it can get a little bit crowded, so I definitely recommend putting your questions into the separate Q&A feature. So that's pretty much it. On the logistics, if you have any other questions, pop it in the chat and I'll be helping out today and moderating some of those questions. And for now, very excited to turn it over for a minute to my colleague, Chelsea.
Cool, thanks, Stacey. So just a couple of remarks before we get started. I'm really excited about today. Everyone agrees that we should be driving towards safer roads and reduced congestion. And I have to apologize, there might be some puns throughout, but the path to get there involves some complex technologies and data flows. The public and policymakers are reasonably confused about what cars are capable of because the terms used to describe the assistive and automated vehicle technologies is not really based on any one standard. Each manufacturer has their own name for the capabilities for branding purposes. Experts have their own terminology, and then there's what the media reports. So all of the automation systems available in cars for sale in the US now are intended to assist a human driver who must be aware and in control at all times. There are other vehicles and robots operating on testing roads or on public roads at higher automation capabilities and by teleoperational remote, but these vehicles are not available for sale to the public. They're just being used for testing purposes or to make goods deliveries. In today's masterclass, we're going to discuss what a connected car is, what it means when someone says their car is level 2, and how cars can see objects on the road. We're going to be giving you a 101 guide to the technologies that make up the connected cars and automation in vehicles. We will also discuss some applications and use cases. Throughout the entire presentation, you'll gain an understanding of the types of data collected and the data flows. And I personally think it's interesting that in this space, the technology is driving the policy in terms of privacy, for example, but the policy is also driving the technology in terms of safety, for example. Near the end of our masterclass session today, we'll touch on some policy approaches, but as Stacey mentioned, we're not here to support one policy approach over another, but we hope by ending on this note, we'll round out today's discussion so that all of you leave here with a better understanding of the technologies and the privacy implications. So with that said, I'm really excited to turn to Bryant.
Oh, thank you so much, Chelsea. Thank you so much, Stacey. I'm really delighted to be here. I'm looking at these photos and it reminds me of the time when I could get a haircut. Sadly, that time is long ago. So sorry for having to look at me today, but let's get into it. We have so much to talk about. As Chelsea mentioned, we're going to talk not just about automated driving and connected driving, but remote driving and driver assistance and everything under the sun. To start that, I want to go back to a video from a few years ago, the first automated driving attack ad.
Technology is great, but driverless cars? Is this really a priority for our state? Well, it was a priority for Jeff Brandes.
I had to convince the Senate it wasn't witchcraft.
He's more interested in legalizing driverless remote-controlled cars and allowing the new Howard Franklin to be a toll bridge than fixing our economy. You would think he'd focus on jobs. Let's stop Jeff Brandes and his out-of-touch priorities.
So, driverless remote-controlled cars. No, it's not witchcraft. And in fact, that attack ad was unsuccessful. The state senator against whom it was directed won his primary and has continued to advance automated driving legislation in Florida. But I bring that up because so much of the terminology is laden with assumptions and misconceptions and straight out errors. Driverless remote controlled cars. There is really no such thing, and at many different levels. What we're actually going to talk about are these 4 categories: driver assistance systems, automated driving systems, remote driving, and connected driving, and really try to break those down. So let's start on our path of increasing automation and connectivity with driver assistance. And we can start not in this century, but the last one. For those of you in the US, you might be familiar with Oldsmobile at all, no longer in existence. At the time, they were projecting a futuristic vibe. This is not your father's Oldsmobile, they said. But imagine a car from the mid-90s, early 90s, has very little of the technologies that are most visible, at least, in cars today. Contrast that with all of the features that, if you have a hefty checkbook, you can buy today. This site, mycardoeswhat.org, is a project of the University of Iowa and the US federal government. It's worth checking out for all of the different features that you might be aware of, you might not be on cars. And they include things like adaptive cruise control, various forms of lane keeping assistance, all kinds of warnings, some kinds of emergency intervention. The list goes on and on and on. Now, there are other attempts to categorize and evaluate these. Euro NCAP is quite a bit ahead of the equivalent in the US, NCAP, or Stars on Cars, in that a number of these advanced assistance systems and emergency systems are included within Euro NCAP's ratings. For pedestrians, cyclists, car-to-car braking, as well as monitoring occupant speeds, lane departure. That's very early in the US. They're merely recommended technologies rather than evaluated ones. So these are a lot of technologies, right? A lot of little logos. And that, as Chelsea's mentioned, has given way to all kinds of different terms. So you're going to hear terms like Advanced Driver Assistance System, or ADAS, Active Safety System. I did not spell out that initialism. Driver support features, Automated Emergency Intervention Systems, AEIS. All of these are within this universe of what we can talk about as driver assistance or driver support. That begs the question, well, what do we mean by driving? Now, even more precisely, we could say performing the dynamic driving task, or the DDT, but in general colloquial terms, when we're talking about driving in a more narrow sense, driving involves paying attention to your vehicle, the road, and the driving environment so that you can steer, brake, accelerate, and communicate as needed. As Chelsea said, if you're expected to pay attention, you are still driving, even when a driver assistance feature is assisting you with steering or braking or accelerating or communicating. You are still the driver in a technical and a legal sense. So that's the working definition that I will use of driving throughout this. And again, it corresponds to the more technical sense of performing the dynamic driving task, even though driving may have an even broader legal meaning and in some cases a broader technical meaning. Now, I get this phrase, performing the dynamic driving task, from SAE J3016. This is a recommended practice by the organization formerly known as the Society of Automotive and Aerospace Engineers. In collaboration with the International Standards Organization, this is going to be released in an even more international multilateral publication soon. It is a widely adopted document. It is beloved and it is hated. The foundation are key definitions for driving automation, including the famous or notorious levels of driving automation, level 0 through level 5. These have varied in time. In Germany, there was a slightly different set of levels and names. In the US, briefly, the federal government had a slightly different set of names. Those have now largely coalesced around at least the numerical level 0 through 5, under which levels 0 through 2 are driver assistance, or what will soon be called driver support, and levels 3 to 5 are automated driving. So in the context of assisted driving, let's start getting into those definitions. So at level 0, you are driving, full stop, no ifs, ands, or buts. Technically, level 0 can include conventional cruise control, where you press a button and your car is going to go the same speed no matter what it runs over. But it is the kind of driving you're used to, even if there are warning and basic safety systems. At level 1, you are still driving, but you're assisted with either steering, for example, lane keeping assistance that will keep your car in theory within the lane, or you're assisted with speed through, for example, adaptive cruise control that will adjust the speed of the vehicle so that you don't strike the vehicle in front of you. At level 2, these what are called lateral and longitudinal systems are combined. So you're driving, but you're assisted with both steering and speed. And that could be because you're using a single feature that does both steering and speed, or you've independently toggled lane keeping and adaptive cruise control. And so functionally, the vehicle through 2 separate systems is doing both. But once again, you are still driving. So let's give some examples of this level 2, because level 2 is the current pinnacle of commercially available technology, the kind of systems that you can buy on a vehicle today. So that could be, as I mentioned, adaptive cruise control plus lane keeping assist. It could be an advanced automated parking feature that does both speed and steering. GM has introduced Super Cruise, which on a limited set of freeways will both direct your speed and your direction, provided that you as the driver are paying attention. And Tesla has introduced and marketed its autopilot and full self-driving capability. I thought that term deserved not 1 set of quotation marks, but 3. For the reasons that we'll talk about, it is in no way self-driving. While autopilot may be an appropriate term from the aviation context, it also tends to increase the expectations for that system beyond what Tesla itself promises and disclaims. But all of these systems are level 2, which is to say they are not automated driving, they are driver assistance. Another feature that's within Tesla's package is what it calls Smart Summon. I'll show you this in action. Pay attention to the car on your left and the not pedestrian, but driver on your right. So no one is in that vehicle. It is being supervised and controlled by Judd, famous YouTuber, who will tell the vehicle if it needs to stop, if it does not do so on its own. So that sort of looks like the car's driving itself, right? Because there's no one in it. The car itself was accelerating and steering and braking. Judd just overrode it when it wasn't doing it as confidently as he wanted. It's still level 2 because if you're expected to pay attention, you're still driving. And fortunately, Judd was paying attention. The key for driver assistance features, and this is really the fundamental part of the definition, is they work unless and until they don't. So a driver assistance system that fails to see a fire truck is in one sense definitionally still working because the developer, the manufacturer, hasn't promised anything more. The expectation is that the human driver will watch, will step in, will intervene when the driver assistance system doesn't see something. Tesla's autopilot system had the pesky habit of crashing into fire trucks, so much so that the National Transportation Safety Board in the US investigated. It, in one sense, was clearly a failure of the system. In another sense, it was the system performing as promised. It will work unless and until it doesn't, unless and until it hits that fire truck because the human driver did not intervene. So I emphasize this role of the human driver in part for safety and in part to highlight that a lot of these driver assistance systems are complemented by interior sensors. sensors that traditionally can detect occupancy, weight, or seatbelt use. Increasingly, that can detect inattention or distraction, or drowsiness, or your failure to keep your hands on the wheel. A lot of these systems use presence and torque monitors on the steering wheel. Some use cameras like GM's Super Cruise and potentially Tesla's autopilot. There are other potential sensors as well for intoxication. This is aftermarket, but under serious consideration for some kind of mandate within Europe. Tesla has at least suggested the possibility of using cameras for internal break-ins. Bosch has suggested using built-in cameras for gesture control, presumably of the radio, not typically of the steering wheel, I hope. And for years, originally GM's OnStar would use the microphone for post-crash assessments to actually communicate with people inside the vehicle, figure out what's going on. So that's all within the realm of driver assistance, and we can even say advanced driver assistance. Where does it then jump over to automated driving?
So Brian, before we get into level 3, I have a question, and maybe some people in the audience are also wondering this. Why are some companies calling their cars level 2 plus or level 2 plus plus? How does that fit into the levels?
Yeah, they're doing that in part because they want to irritate a few people who wrote SAE J3016. And they're doing that largely for marketing. So J3016, the technical document I alluded to, is very clear that there's no such thing as half a level. There's no such thing as a 2-3 or a 2 plus or a 2 AAA. It's either 2 or it's 3. And that's because the expectations for 2 are unchanged. The expectations for the system and the expectations for the driver. Nonetheless, even 2 is a pretty wide threshold. So it could be a adaptive cruise control that works under very limited freeway conditions, plus a lane keeping system that would ping you back and forth between your lane, right? You go to the right and you go back to the left and you go back to the right. And that would technically be a level 2. It could also be something that is much more advanced in some contexts, like GM Super Cruise or Tesla's autopilot, that does a lot more of the driving under more circumstances. And so companies want to distinguish themselves for what they see as superior systems. In the same way that if you reference the cellular world, you'll see all kinds of pseudo 5Gs or LTE triple pluses. It's a nod to the technical world with most of the gaze fixed on marketing. Does that you think speak to that?
I think that's great. Thank you for that.
Cool. Sure. Everyone would really love to say it's 3, but it's not, because at the point that a company says our system is level 3, what they are saying is, you user are no longer the driver. We don't expect you to pay attention. And that's very scary for a lot of companies, for a good reason, because that demands a level of confidence in the system that very few companies are able to credibly claim at this point. So automated driving often is referred to as autonomous or driverless or self-driving. You can get into lots of nomenclature debates and fights with a lot of dorks like me. We can do that for hours afterwards. For those of you in the legal and policy worlds, I'll note that automated driving is something of a shibboleth in at least the automotive technical world. Meaning, if you say automated driving, you're signaling that you are aware of technical language. If you say autonomous driverless or self-driving, you're probably speaking more to a public, and you're signaling to the technical community that you may not bring that level of understanding. This is debated within particularly computer computer science, autonomous is still quite popular. Automated driving is also a mostly neutral and more inclusive term. Driverless and self-driving suggest certain technical and legal conclusions. Let me give you an example of why this gets so complicated, why I say an inclusive term. This is a pretty famous chart of the levels of driving automation. Don't even try to read it. You'll quickly fall asleep. ODD specific execution, fallback ready user, DDD fallback, OEDR. It's indecipherable, even though it's in fact a summary of our 35-page document. So we put this out at SAE and thought, well, you know, that'll be clear. And they said, well, it's not really clear. So what if we add this chart? That'll help people understand the levels. We said, well, all right, that helps, but that's not really clear. So let's add this chart. That'll explain to everyone what the difference is between all these levels. That'll make it clear. Didn't quite. Said, well, all right, how about this flow chart? That'll explain the differences. No, all right, then how about this one? Surely this will help people understand all of the various iterations. Note that this is, by the way, the simplified logic flow diagram. These are all efforts to explain what are 6 levels of automation. 0 is a level. Now, I'm kind of making fun of engineers. I'm an engineer, but just as an aside, I'll make fun of lawyers too. This is what we finally ended up with. You can find this online. It's worth looking at, but I'm actually going to talk through my own gloss on these levels. But just a note about lawyers, in case you're laughing too much engineers. In many of our US states, we have legal definitions in our code of drive and operate that are indecipherable. In Maryland, drive means to drive. Thank you for that. And to operate. Operate means to drive. And operating is broader than driving. So drive is broader than operate is broader than drive. Are you dizzy yet? You should be. I am. This is the reality of our technical and our legal worlds. There is a lot of ambiguity, there's a lot of confusion, and there's frankly a lot of complexity. So let's try to break that complexity down for automated driving. Recall, we've already talked about the 3 levels of assisted driving, levels 0 through 2. The automated driving features also have these 3 levels. At level 3, you are not driving, but you will need to drive if prompted to do so in order to maintain safety. So the extreme example is, if you don't want to go off that bridge, you better be able to drive within a reasonable time after the system asks for your help. At level 4, you're not driving, but either you will need to drive if prompted in order to reach your destination, not for safety, but to get where you're trying to go. That's in a vehicle you can drive, or you will not be able to reach every destination. That's in a vehicle that you can't drive. And I'll talk through what those mean. And at level 5, you're not driving and you can go anywhere. So let's look at what this means. And first, I want to just highlight the term ADS, or automated driving system. You'll hear that a lot. The technical phrase is a vehicle equipped with an automated driving system that is engaged or is not engaged. That is a mouthful, so even though it makes the folks at J3016 sad, I will talk about an automated vehicle, an AV. So with that, let's look at level 3, where you are not driving, but you will need to drive if prompted in order to maintain safety. This feature was briefly available in Europe on a small number of Audis for people who had tens of thousands of euros. Audi announced plans to deploy it elsewhere, and then very recently quit this business and said, we are not going to be deploying our level 3 feature. So it was a very brief moment of level 3 automated driving. What did that, and you're welcome to ask me why, by the way, that all that happened. But what did it do? So under limited freeway conditions at slow speeds, in other words, a traffic jam, the vehicle would follow other vehicles, stay in the lane with a confidence great enough for Audi to say, you user do not have to pay attention. At the point that traffic started speeding up again and the vehicle was about to exceed its threshold, roughly 30 miles an hour, 60 some kilometers an hour, the system would say, user, please start driving again because I'm not going to drive anymore. So let's look at this in very crude animation. Another situation would be if the weather conditions exceeded what the sensors or system could deal with. Again, there would be an alert, user, please start driving again because I'm not going to. And the expectation would be that you as the user would start driving, would resume driving. If not, the vehicle would simply come to a stop in an active lane of traffic, put on its flashers, make life uncomfortable for the driver, but that would be the end of its system. So watch the red car, realizes there's weather, it tells the driver to intervene, the driver doesn't, and it stops in the lane of traffic. That's the expectation for level 3. It does not need to do more than that. Now contrast that with level 4. Recall our first scenario, you're not driving, but you will need to drive if prompted in order to reach your destination. So this could be eventually a feature on a ordinary production vehicle, the kind that you can buy. Let's say it's a freeway system, you would engage it on the same kind of freeway, but let's say it can't deal with heavy snow. So once again, the vehicle recognizes that there will be a condition it can't deal with, tells the driver to resume driving, but if the driver doesn't resume, rather than stop in the lane, the vehicle will reach what's called a minimal risk condition. So in this circumstance with a wide freeway shoulder, it's generally agreed that stopping on this shoulder outside of the active lane of traffic would be a minimal risk condition, a reasonably safe spot where the vehicle could stop if the human does not resume driving. And that's what makes it level 4, its ability to achieve this. Now recall the second prong of level 4 is, you're not driving, but you're not going to be able to reach every destination. That's because some vehicles with this planned level 4 feature are not all-purpose road vehicles. They might be a low-speed shuttle, or a taxi limited in certain areas. And that means that you're never going to have to drive, but you're not going to get from Paris to Oslo sitting in one of these things. So I've mentioned a few times these kinds of limitations. Might not deal with snow. It might not deal with speeds at freeway free flow. It might only be limited to freeways. It might only be limited to a residential neighborhood or even sidewalks. It might only be limited to a suburb outside of Phoenix because that's where a company has developed confidence in their maps. These limitations are referred to as the operational design domain, the ODD. This is a key term that is as important as the levels of automation, but gets a lot less attention. It is when and where a feature is specifically designed to function. And you can have an ODD for a driver assistance system. You can have an ODD for a level 3 or a level 4 system. You don't have an ODD for a level 5, or phrased differently, there is an unlimited ODD because at level 5, you're not driving and you can reach any destination under conditions that a human driver could manage. So the vehicle will go through a city street, it will go on a freeway, it will go during the night, the day, it will go through snow, it will be that famous post officer who goes despite the conditions. And in this way, level 5 is really considered by those pursuing automation to be the holy grail. It is the as yet unattainable ideal that is by many people's reckoning years or decades, if that, away, because of the vast number of conditions that these systems have to confidently and reliably deal with. So really, so much of the discussion about automated driving is going to collapse into level 4, because a lot of companies are hesitant about level 3, and level 5 is seen as very distant. So those were the levels of automated driving, and typically they're used to describe a vehicle feature. Right? A single vehicle could have a level 2 feature and a level 3 feature and a level 4 feature based on the particular operational design domain. But we can also talk about vehicle types, vehicles that you can drive in the conventional sense, those with the steering wheel, and those that you can't. You think you get in, you press a push button, and you go. Likewise, we can talk about trip types. So maybe you taking a trip where you have to drive for the entire trip. That's pretty conventional. That's all you can do in a vehicle you can buy today. Above that, we reach the trip types that involve automated driving. You may need to drive at some point if prompted to maintain safety. That's level 3. You may need to drive if prompted to reach your destination. That's level 4. You won't need to drive, but you may drive if you want. That can correspond to some level 4 and level 5 systems. And you'll not need to drive for any reason, and you may not drive. Think about the vehicles that you can't drive. That would be, again, a level 4 or potentially a level 5 system. So what's driving today? To reiterate Chelsea's point, you cannot buy an automated vehicle. You might be able to ride in an aspirational automated vehicle. That is one that a developer is testing with the hope that it will be automated. You might be able to use a delivery robot that will typically not be on road and hence technically fall outside the levels of automation. But each of these will almost certainly be supervised in some form. What does that mean? Well, to give you an aviation example, and aviation examples are useful again unless and until they aren't. Imagine getting on a plane and hearing your pilot say, "Hi folks, just wanted to let you know today we'll be using autopilot. Have a nice flight." That's pretty normal, right? Contrast that with getting on a plane and hearing the pilot say, "Hi folks, I just want to let you know that today you'll be using autopilot because I'm getting off. Goodbye, have a nice flight." There is a really big difference between those. And so one of the key questions that often gets missed in talking about demonstration systems or reacher systems or announcements is there some form of supervision? Or is the company confident enough to say, for better or worse, our system is so capable and reliable that we don't need a human monitoring it inside or outside the vehicle? There are 2 examples of systems that have been deployed in fairly limited ways that do not have necessarily in-vehicle or vehicle-adjacent monitors. One is Starship and some similar systems with delivery robots that generally use sidewalks, bike paths, and have some form of remote monitoring. The other is Waymo, formerly Google's self-driving car project, which has publicly announced that some of the trips they have offered to a small number of select users have taken place without an in-vehicle safety driver and without the kind of direct, immediate, permanent monitoring that might characterize remote driving. But these companies tend to be very vague about what this remote human role actually involves. We'll talk a little bit about that shortly. So looking ahead, like what's coming down, I think we'll see automated driving deployments, but they'll be with some combination of slow speeds, simple environments, and at least semi-supervised operations. It's my rule of 3 S's. I think you're going to need about 2 of the 3 initially. Right, so that was automated driving, but you can see I already started to allude to this notion of a driver or somebody beyond the vehicle. And that brings us to remote driving. You've already seen Tesla's Smart Summon. That's an example of remote driving. Our driver is here on the right, monitoring the vehicle, intervening as it drives. Platooning is arguably a form of remote driving where a lead driver in the front vehicle is making decisions that are then communicated wirelessly to the vehicles that are following at a very close distance. And so they behave, in effect, as a convoy. The first driver steers to the right, the other vehicles follow. The first driver brakes, the other vehicles brake. Fun trivia question. In these platoons, which can offer significant fuel savings and are still very experimental at this point, different trucks can have different braking performance. Would you put the truck with the best brakes in the front or the back? Consider and answer in chat. All right, so an even more remote form of remote driving is one that's been pioneered by several companies, probably the most prominent of which was Starsky Robotics, which had a vision of using some combination of automation and remote or teleoperation to operate large trucks on freeways up to the factories or warehouses. Starsky shut down just a couple months ago. All right, so now that we've talked about automated driving and remote driving, I want to give you a pop quiz. It will be graded. I am a professor. Imagine on reaching a crash site, an automated vehicle stops in its lane until someone at a faraway monitoring center sketches its path. Using its sensors, the vehicle then follows this path. Let's take a look at this. When FPF offers a masterclass on graphic design, please sign me up. I clearly need it. So what is that? Is this level 3 or level 4 remote automated driving? And is there a remote driver? What do you think? So the vehicle stops in its lane, calls for help, an operator sketches a travel path, but then the vehicle then roughly follows this path using its own sensors. Level 3 and level 4, and is there a remote driver? All right, so on this first question, level 3 or level 4? The key question seems to be, is standing in this lane a minimal risk condition? And you're going to get arguments. Yes, it is. That's what a human would do. There's no better place to go. You're not going to pull off on this narrow shoulder. You're also going to say, well, no, a human wouldn't need to stop. They would simply slowly go around. And so this is not actually a minimal risk condition. This is an example of how these nice, neat, clean levels are actually pretty confusing. And the proper classification ultimately comes down to disagreements or decisions about what terms like ODD or minimal risk condition really mean. Second part of this, is there a remote driver? Well, here we would ask, is the remote agent performing the dynamic driving task? Or are they merely providing additional information for the automated driving system in the same way that a police officer gesturing would provide additional information, or a pedestrian signaling they were going to step out would provide additional information? And here the consensus seems to be that under this circumstance, there's not a remote driver. There's merely a remote agent who is facilitating the driving task, but not actually driving. You can debate that too. All right, so that wraps up remote driving and brings us to connected driving. Oh, this gets complicated too. By introduction, I want to emphasize that automation and connectivity are orthogonal, right? One's like the y-axis, the other's like the x-axis. And so if we put your father's Oldsmobile, this 1990s car, way at 0, 0, we've been talking so far in terms of assistance and automation of increasing automation. Level 1, level 2, level 4, potentially level 5. And I mentioned level 5 is this holy grail. Connectivity is different. It's how a vehicle communicates with others. And that can happen at any level of automation, albeit in different ways. And so really the far right point of this graph isn't the holy grail. I'm going to call it a unicorn because it really involves all kinds of beautiful fantasy. And we are in no way there yet. So now we're going to talk about this x-axis of increasing connectivity toward what is broadly described as V to X. What is V to X? V to X is vehicle to everything communication. And there are all sorts of other acronyms within that, the most common of which are vehicle to vehicle, it's V to V, and vehicle to infrastructure communication, where a vehicle is talking directly with another vehicle or talking directly with roadside infrastructure like traffic signals or cameras or other sensors. And there are lots of others, and broadly we just call them V to X. So I want to first talk about this narrow version of vehicle connectivity, that it typically involves direct communication to and from these vehicles. The vision is for really fast communication. We'd call that low latency, and super reliable communication. Why really fast and super reliable? So that it can support safety critical applications. So for example, in this graphic, we see how a truck is barreling down a road with no intention of stopping at our stop sign. Another vehicle recognizes this and immediately communicates to the vehicle coming from the left that they should stop because they will be hit otherwise. There, you're going to need to speak in milliseconds, and it's not enough to say, you know, the phone line was down. These are messages that need to be conveyed immediately and confidently. In the US, the vision for how some of these messages would be conveyed is a basic safety message that would roughly 10 times a second provide theoretically anonymized data from a vehicle about its speed, its position, its basic characteristics. In other words, hey there, vehicle neighbors. My temporary pseudonym is, Big Sister 389. I'm a 15-foot long vehicle at 34 degrees, 81 degrees, lawn lad, 300 feet elevation, moving northwest at 30 miles an hour, but slowing at 15 feet per second with my steering wheel at 15 degrees and my brakes engaged. Right, and you say that 10 times a second, really fast. You can all practice it now, I'll wait. Everyone within, say, 1,000 feet hears that, and that might be very useful for them to know. And then every few seconds, the vehicle might add some additional information. I'd like to know, it's 32 degrees outside, my lights and wipers are on, I weigh 3,000 pounds, and here's some other stuff. Oh, wait, there's black ice. The EU has something called the CAM, the Cooperative Awareness Message. This is, again, defined in protocol. That's vaguely similar. The frequency is different. The content is a little different. The acronym is nicer to pronounce, but longer to spell out. And this brings me to the point that the devil for this narrow sense of connectivity is really in the details. Why? First, there are two competing technologies. One of the big questions is, which set of technologies will industry and governments coalesce around? Will they use something that's called DSRC or in the US or ITS-G5 in Europe, dedicated short range communications? It's a Wi-Fi protocol. It's been around for a very long time. We're talking over decades. Or will industry and government coalesce along the CV to X, that cellular V to X standard for both LTE and 5G. This is a cellular based standard. It's newer. There are some putative reliability, speed, security advantages. But so much of this discussion is grounded in sunk costs or grounded in financial competitive incentives. There is so much money to be lost and made, particularly among the companies that are advancing these particular protocols. So it gets really messy really fast. This is compounded by debates, particularly in the US, over spectrum reallocation and spectrum sharing. With a view toward DSRC, a portion of the wireless spectrum has since the 20th century, late 20th century, been set aside for ground transportation communication. DSRC has barely been implemented, and so it's been a vast empty spectrum that has looked very appealing for the companies that would like to do more internet. And by extension, for those of us who would like to watch more cat videos. So yes, I'm afraid that in one view, the tension here is between roadway safety and more cat videos that we can all watch. This isn't the only view. There's another view that, as I mentioned, all of this is orthogonal to automation and ultimately will not be a big piece of vehicle technologies. That this narrow sense of vehicle communication is neither necessary nor sufficient for automation, and others dispute the extent to which it would be helpful for safety. But the reality at this point is that implementation of either is really few and quite literally far between. When the first phone was invented, you really had no one to call. And so even though GM has put DSRC on some Cadillacs since 2017, how often do you encounter another Cadillac driving around? There's just really no one to talk with. Some VW Golfs will have DSRC from 2020. Some, in fact, mini cars in Japan have had this technology since 2016. In contrast, Ford has recently announced that all Fords, at least in the US, will have the CV2X radios from 2022. We'll see if that happens. DSRC was expected to be mandated in the US a few years ago. That did not happen, really under multiple administrations. For a few months, it was the preferred technology in the EU until the Council of Europe mandated a new standard that would be technology neutral, that is, would not pick a winner between the two, although there was some suggestion that by unpicking DSRC, it was implicitly picking CV2X. Again, this is very different from automation. It should not be confused with automation. When we start talking about the sensors, I'll give you another example. Why? Now, there's a broader version of vehicle connectivity that doesn't talk about DSRC and CV2X or this kind of super high speed, super reliable communication directly between vehicles or with infrastructure. And that's the kind of technologies that are on our vehicles today, from basic telematics to infotainment, to dongles that plug into your onboard diagnostics port and can transmit information about your vehicle's performance, to in-vehicle Wi-Fi or Bluetooth, to mobile vehicle apps that can let you monitor your car or start your car or unlock your car or unlock somebody else's rental car from the convenience of your phone, over-the-air updates, which have been offered on infotainment systems for a while, but which have been really only offered by Tesla for the kind of safety critical vehicle movement systems. And systems like OnStar and other driver systems that for years have connected drivers with the outside world. All of this is here now, and in fact has been for years. And it's a really important point when we start talking about the interplay between automation and connectivity and all the data and data protection and privacy issues that involves. So as a preview for that discussion and as a way of giving you some food for thought toward the break, I want to identify 3 key questions for thinking about data in the context of automation and connectivity. The first is, are mobile phones and other connected devices different than motor vehicles? And if so, how? Why should it make a difference for regulation? Secondly, are vehicle-to-vehicle communication capable motor vehicles different than conventional motor vehicles for the purposes of data? If so, how and why does it matter for regulation? And then finally, are automated vehicles different than conventional motor vehicles for the purposes of data? And if so, how and why? And I'm not suggesting there's actually a right answer to these questions. So much of these categories, as we've talked about, exist on spectra. But as we start thinking about classifications for the purpose of regulation, these are valuable threshold questions. Right. So those were my introductory slides on these 4 categories of automation and connectivity: driver assistance, automated driving, remote driving, and connected driving. And I think we're going to do some discussion and questions. Then when we come back, we'll spend some time focusing on automated driving, particularly the technologies that underlie object detection and classification and its implications for data. But with that, Chelsea, I will turn it back over to you.
Sure, thanks. Sorry, I'm just answering a question in the chat, so a bit distracted.
That's okay. We have driver monitoring systems for that very thing.
Cool. So are we ready to go on to the switch screens?
I think we're taking a quick break here for questions, if we have any. We had a few folks put their questions in the Q&A as we went along, and I think we were able to answer some of those as we went along. Thanks, Brian, and thanks to people who put questions in the chat. Let's just give it a moment here. I want everybody to be able to digest. That was a lot of information. That was awesome. Take a moment if there are any questions now before we go on.
It was a lot of data, which is appropriate for an organization focused on data.
Yeah, and as people think about that, let me just start off with one of the questions that I had, Brian, which was when you were talking about some of the different technologies that are being adopted in the EU and in the US, you mentioned that there are a lot of issues related to sunk costs and financial incentives and competitive incentives. Aside from those, are there clear benefits or costs, objectively speaking, to using one kind of technology over the other, or is it just a question of having sufficient adoption?
Yeah, it's the kind of question that you'll get different technical answers on. And so if I were to give my view of the 2 competing technologies, it would be an incomplete view. And the difficulty with reaching a confident answer in this area is that there's so much financial pressure behind this. And so a lot of the most tempting sources of information are going to be those that have a financial interest in the outcome, which is not to diminish the quality of the information that they provide, but to recognize that so much of this is wrapped up with an agenda, one that's compelled by financial considerations. There are some companies that have at least suggested that they might deploy radios that are compatible with both, but that's been analogized to speaking 2 languages. That is, if we're building a new system, it's probably best if we choose one language rather than saying, well, our language is going to be both French and English, because you might not speak French. Apologies to Canada, Chelsea, I know you're there. The DSRC protocol is generally regarded as older. And so CV to X is believed to have more expansion possibilities. It's one that might continue to grow and evolve. And yet so much research, particularly on spectrum and implementation, has been done on DSRC. Some companies have deployed in DSRC. Some communities, particularly in the US, have begun deploying infrastructure based on DSRC. So for example, traffic signal radios. to communicate signals to cars. It's a difficult debate, and it's one reason why some people say we're just going to skip over this, and automation is going to have to learn to do all of this without reliance on this kind of immediate communication. The other consideration here is that there are all kinds of messages that are not safety critical on the order of milliseconds that can be communicated in other ways. And the example of that is Waze, quite literally, WAZE, and other private app-based systems that will collect crowd-based data and will share it with drivers or users. Those systems rely on basic cellular networks that do not have the speed or the reliability that we might need for a warning that I'm going through the stop sign, but they have been sufficient for warnings, bad weather up ahead, traffic jam up ahead, those kinds of systems. How is that for a descriptive, slightly predictive, non-normative answer?
I think that's great. Chelsea, do you want to add anything?
Yeah, there are a couple of really good questions in the chat. How will the pandemic alter development of these topics? That's something I'm interested in. I've been kind of following how that has impacted. I think one really obvious way is the not wanting to be around other humans factor. So you're seeing like delivery robots, not necessarily more available because you can't speed up the technology. It is where it's at where it's at, but more of the demand and seeing that use case as viable. And then also the ride share, people may be hesitant to share with other people that they don't know. So it's kind of too soon to tell what's going to happen later. But I think companies are thinking about different ways to sanitize and offer those different options. I don't know, Bryant, if you have any comments on that?
Yeah, I think the pandemic has been very sobering for the state of the technologies because there are all these applications where they really would have been great in if we had designed them for that and if they were a little more advanced, right? Managing a city in the absence of humans. But this has also shown us how brittle and inchoate, that is underdeveloped, these systems are, where it's still much easier to just put a human. You might send a package down the road, but you're still going to have a human following behind this vehicle monitoring it. And I think that's been a important reality check for these systems, that in the unexpected, they're not going to be as flexible as a human for a long time. And that could be as true for future evacuation in a hurricane as for a pandemic. In terms of the impact on the technologies, Chelsea, you talked about how it's highlighted the potential of some applications like delivery and potentially given some hesitation to others like shared ride services. I might take a bit of a divergent view here from many people who've commented on this, but I don't think it's dramatically slowed the development of the technologies. It was probably healthy to have some sort of break for all the smart engineers to think about some things other than on-road tests. There's a lot that can be accomplished by simulation. I think companies have found ways to put their vehicles back on the road in the service of humanitarian missions. And my expectation is that we're going to see actually this pandemic used more as an excuse for the slow speed than as a genuine explanation. Automated driving has been 20 years away since the 1930s. In the 30s, we had it by the 50s, and the 90s, we're gonna have it by today. For the last 10 years or so, it's been 5 years away. And even then, the pace has been slower than a lot of folks, including me, expected. And so I think when we see companies go under or companies delay their announcements, they'll cite the pandemic, but it will really be that same story of slow technological development.
Mm-hmm. That makes sense. I want to go back to the connected cars or like smartphones on wheels analogy, because we see and hear that a lot, and someone in the chat brought that up. this is probably a huge topic. We could spend a lot of time on it. I have a couple thoughts. Like usually with your smartphone, you're the owner, you're the user, whereas with a vehicle, could be potentially many users, occupants inside as well as outside pedestrians. So the data flow aspect is different from a personal device. Also, when you think about how smartphones and vehicles are developed, so the research development time for vehicles usually is much longer. There's a lot of safety aspects to consider. So the manufacturing from both of those is can be quite different. Usually when the manufacturers have a vehicle on the production line, like everything is set, it's not so easy to just go in and quickly make a change. It might not be as nimble as the smartphone sphere. So what are your thoughts on that, Bryant?
Yeah, it's harder to take the battery out of my car at 100 kilometers an hour going down the freeway than it is to hard reset my phone. These vehicles, as we'll talk about in the next section, that actually might be a nice segue to our second section, have just tremendous computing potential onboard and offboard, although they're also subject to limits that don't get discussed enough, whether that's actually the battery power on board a vehicle or the ability to transfer large amounts of data off board. It's still in some ways easier to just do that physically than it would be wirelessly or even wired. But as I'll discuss, the combination of sensors, computing, and connectivity really unlocks potentially undreamed of possibilities, good and bad, for these systems.
Cool. I think on that note, let's jump right into the next section.
Great. All right. So on that, let's go to our next section. So previously, as I mentioned, we talked about these 4 categories of automated driving, 4 categories of driving: assisted driving, automated driving, remote driving, and connected driving.
Oh, I don't think, at least I can't see your screen.
Yeah, we're going to launch it right here. I wanted to get to the right slide there. Thank you. So that should be good. All right. So in this section, I'd like to focus specifically on automated driving, the technologies in particular, computer vision, perception, and introduce the data considerations. And to start with, I'm going to talk about how the technologies underlying automated driving work. And I'm emphasizing technologies plural, because automated driving is not a single technology. It's not a single approach. In fact, automated driving is a wide range of underlying technologies, applications of those technologies, business cases for those applications, and participants in those business cases. It's very tempting to talk about the competitors in this field, or the putative competitors, Waymo, Uber, the automotive companies, and say, well, which one is going to do it first? And the reality is that all of these efforts involve complex partnerships among companies whose names we know and companies whose names are less obvious, even if they're very important in the field. And so we're going to see these networks of efforts. That's important from a regulatory perspective, from a technical perspective, and from a data perspective, as we can discuss. So recall that we talked about what driving means, at least for our purposes of performing the dynamic driving task. Paying attention to the vehicle, the road, and the environment so you can steer, brake, accelerate, and communicate as needed. So what does that involve? Well, you as a driver say, well, what's around me? What should I do? What should I do about it? And then I'm doing it. Right? That's roughly perception, planning, or more narrowly path planning, and actuation. And these are three of the big areas for automated driving development. Actuation needs to be really reliable. You better make sure that you can engage that brake. You have multiple ways of engaging that brake. That's not as technically complicated as the first two. What's around me and what should I do? For our purposes, I'm going to focus on the perception because that's really where a lot of the data and privacy questions arise. But it's also a predicate for the path planning. To know where you're going to go, you need to know what's around. So I mentioned that there are all kinds of technologies and applications and in companies. This is a picture of Waymo's retrofitted Chrysler minivan. So there are alternatives, there are alternative designs, or alternative sensor suites, but let's start with this one. Waymo's vehicles use cameras, high definition cameras that can achieve the kind of perception that we can with our eyes and then some, including giving a sense of depth, including a sense of detail. But in addition to cameras, Waymo uses radar. Many of your vehicles today have radar. This is an active sensor, so a camera perceives light that comes in, radar sends out radio waves and sees what bounces back, and the light or laser equivalent, which is LiDAR, likewise an active sensor that sends light out and sees what bounces back. In addition, Waymo uses microphones. Why? Well, you want to be able to hear an emergency vehicle coming. Ultrasonic sensors that are particularly good for close distance sensing, some inertial sensors that help you figure out where you've gone, and yes, GPS receivers. But as a kind of an afterthought, so often I think people assume that these vehicles are principally using GPS in terms of one of the satellite systems. And that's not actually true. It's a relatively minor part of the sensing. Cameras, LiDAR, radar are really the big three. Now, not everyone uses these. Tesla, for example, has been pretty famous for rejecting LiDAR. And you'll see some of these systems, particularly cameras and radar, on vehicles that you can buy today, although not with necessarily the full performance or the full software support. In addition, Waymo has many of the numerous internal sensors that I described previously that are on cars today. So why so many sensors and why so many different kinds? Well, these sensors need to be able to measure from inches or centimeters away to hundreds of feet or many hundreds of meters away. That's the distance that you need if you're trying to park in a narrow parking spot or you're proceeding down a freeway at 120 kilometers an hour. You're going to need to, at that point, see tens or hundreds of meters away. These systems need to be able to see in the day and the night, sunrise, sunset, when the sun's beaming in at midday, through snow, rain, fog, and glare. They need to be able to capture a range of distance measurements, size, color, detail, to see not just what something is, but how far away it is. And with an appropriate level of accuracy, reliability, and confidence. I mentioned the operational design domain, the ODD, the conditions under which a vehicle can operate. This is why we're likely to see early deployments that have simple environments or slow speeds, because the combination of the physical sensors and the software that supports it is not yet able to deal with this wide range of conditions confidently. It's not just that you can do it once, that you can do that drive 1,000 times, tens of thousands of times without being surprised. So that explains why we as humans have 2 eyes and 2 ears typically, but these cars have so many more sensors. So the first role of these sensors is for mapping. In other words, what do I as the car expect? And the conventional approach for this has been to build highly detailed 3D maps to send a car, that looks like this one out into the world to collect all this data and then to process it through automation and still some human manipulation to identify the static world. Right? Where are the lane lines? Where's the curb? What are the key buildings? What are the signs? What might be the paths within a lane at an intersection that you might take? This is the incredibly complex detailed 3D map that would be generated from this sensor data and then preloaded on vehicles. Then during a drive, the vehicle system can compare that highly detailed 3D map to the real world that it's perceiving contemporaneously with its sensors. And comparing this map allows it to do two things. First, it can say, where am I? Right? Well, I think I'm in Scottsdale because this sure looks a lot like the maps of Scottsdale I have. In fact, I think I'm at this intersection because it's a dead ringer match for this intersection. That's why GPS is actually often secondary. And secondly, this allows the system to figure out what's different. So first of all, what's changed? Is the street still where I expect it to be? And then secondly, what is there to see? What are all the potential dynamic objects, the other road users that I need to sense and identify that are going to be moving around in my world? And then afterwards, based on all these data that are collected, the system can then, the maps can be updated, refined, improved. And ideally, in theory, this will all be shared. It will be dynamic. These systems will be feeding information constantly into the network, and that will improve it for all the road users. That's at least the vision that many of these companies have embraced. Note on that, it's not the vehicles learning in real time and evolving independently of themselves, right? It's collecting data, sending that back, having that data processed, then returning it in a usable form for the next time. This all applies unless you're Tesla, right? I mentioned that Tesla has rather famously rejected LiDAR. They've also suggested that the long-term viability of these systems will lie in being able to navigate an environment with nothing more than you and I have today. Cameras, I guess we can't shoot laser, we can't shoot radar, but that's a part. And a much more rudimentary map, the kind of map you would see on your in-vehicle navigation or on your phone. And that alone should be enough to then allow the vehicle to navigate using its own contemporaneous sensor data. So what are the objects to be seen? This is the other function of these sensors, to detect what are somewhat impolitely called objects, because that typically refers to people who are walking or running or biking, or people who are walking bikes or walking in crowds or trying to cross, as well as all the other road users we'd see, right? Buses, cars, motorcycles, scooters, trucks pulling cars pulling trucks, trailers, as well as animals who might happen onto the road. A lot of different kinds of animals that sure look a lot different, as well as the kind of road users that might not be all that typical: police cars, ambulances, garbage trucks, construction equipment. The conditions that are changing, like construction, crashes, road debris, like mattresses, these are true objects, right? Mattresses, plastic bags, difference between plastic bags and potholes, difference between a tree limb up here and down here, shadows, as well as all of the other things that you might happen to see on a road every million miles or so. Cars going the wrong way, cars that are upside down, all the millions of things that we've seen before and the millions of things that we haven't. This is what's detection, classification, and tracking needs to account for, to figure out what these are, what they mean, and then be able to predict what they'll do next. That's really tough. I'm going to give you an example of something that wasn't all that tough, comparatively speaking, but was very tragic. And this was Uber's 2018 fatal crash in Arizona that resulted in a months-long suspension of its testing. in the evening, when there was nonetheless sufficient visibility, one of Uber's test vehicles, being supervised by an in-vehicle safety driver, struck and killed a pedestrian who was crossing at a place that was not a marked crosswalk on a suburban roadway. She was killed. Why? Well, Uber was developing an automated driving system based on Volvo's production vehicles. And so to do this, Uber had disabled Volvo's emergency braking system. This is one of the driver assistance features that I described previously that would detect a pedestrian and brake, at least when it works. Had that system been engaged, the National Transportation Safety Board concluded that the system would have engaged and braked. But having that system interact with Uber's system would have been potentially messy, could have been dangerous, and might have reduced the amount of information that could have been gained by this testing. So we had only the automated system and the safety driver. 6 seconds before the impact, Uber's software said, well, you know what, there's something over there. I'm not really sure what it is. I think it's an unknown object. No, wait, now I think it's a vehicle. No, wait, now I think it's a bicycle, with various levels of confidence. But because it was jumping between these various objects and it wasn't sure, it kept reclassifying, identifying it, and it did nothing. So for 6 seconds, the system says, oh, there's something, I don't know what it is, but I'm not going to do anything about it because it's changing, because I'm not confident. This was a failure. Just over a second before the impact, the software said, you know what? I'm going to crash. I'm going to hit Ms. Hertzberg. But because this was a test system, recall our pilot sitting in the seat, it did nothing because the design decision was made that it would be better to have a safety driver intervene than to have this system intervene. Why? Because there could be a false positive. That is, the system could perceive an obstacle that doesn't exist, could break suddenly, and that could also be a dangerous situation, right? You get rear-ended, you could create a crash that way. So that was a design decision. Less than a second before the impact, the human safety driver finally intervened. The NTSB concluded that they were very distracted. They were probably watching TV. The result is that a woman died. And there's a design lesson here as well. So believing the safety driver will be careful, Uber's engineers created a vehicle that behaves recklessly. And believing that that vehicle would be careful, Uber's safety driver behaves recklessly. That was a nasty loop that resulted in a preventable fatality. It's unacceptable. This image is much darker than it probably was at the time, and certainly the illumination of vehicles' normal lights combined with the active sensors, radar, LiDAR, high-def camera would have made this evidently detectable long in advance to stop. But you can see here this combination of person and bicycle. This was something that several companies suggested that their systems would have been able to properly identify and classify, but Uber's clearly was not because of this complexity of detection, classification, and tracking. So these systems need to be really, really good so that these kinds of things do not happen. We're all helping. If you've ever done these CAPTCHAs that ask you to identify crosswalks or traffic lights or cars or roads, this is a way of helping to train these systems that are detecting and classifying these objects. If you've done the machine learning session through FPF, you have a sense of this, but this would be a form often of supervised learning where you say to the program, much like you'd say to a dog, do this, do this, do this. It's a traffic signal, it's a traffic signal, it's a traffic signal, it's a traffic signal, until the system starts figuring out that that is in fact a traffic signal, and things like it are a traffic signal. And that's why your dog can bring back balls that are not necessarily the ball that you threw. Contrast that with unsupervised machine learning, which is also used in development. I compare that to a cat. A cat just goes out and brings back a bunch of things, and then you figure out what it is. Like, well, there seems to be these dead carcasses that keep showing up. I guess that's a rabbit. It's a very different form of machine learning. So really what we're talking about is like a thesaurus, that these systems are developing a sense of what is a pedestrian, right? What is a vehicle? And there are these images, these are scenarios that don't quite match, but get close enough that the system can reliably say, I think that that is a pedestrian, even though I've never before seen a pedestrian pushing a bicycle. So some of the driver assistance systems that are on vehicles today, particularly the advanced ones, among those, especially Tesla, use machine learning techniques and do use this form of perception. All automated driving systems are going to use these machine learning techniques and at least some form of this advanced perception. Which means that there is a tremendous amount of data. There's been lots written about the incredible amount of data that vehicles will generate in the future. And vehicle data generated or received is kind of a giant meaningless number, because so much data in today's world, in today's vehicles, in these vehicles of the future, will pass through the system without ever having a usable form, without ever being stored, without ever being transmitted. And so it's more useful to think about data that might be stored on the vehicle and data that might be transmitted from the vehicle off board. In terms of the stored data, when companies are developing these systems, they're storing everything feasible, at least initially. When these systems are deployed, those data storage needs will be much less. Data will still be useful for development, but not as much for all of this basic development. Data will still be transmitted for other uses, for refinement, for offboard processing. And so I think some reasonable predictions are we might see a terabyte, a couple terabytes an hour potentially transmitted if the wireless networks can support that amount of data transfer. This is Wi-Fi or 5G. And that would be equivalent to one of your large home hard drives that has millions of your photos, if you're taking too many photos, or hundreds of thousands of your songs. So what kind of data are these? Well, they might be data to operate the system. The kind of data that you absolutely need to be able to figure out who is a pedestrian, who is a bicyclist. It might be data that are used to develop the system. These would be to further refine, to further develop. Might be data to document performance, either to develop safety cases to be able to show the continuing safety of the system, or to evaluate crashes or incidents after the fact. By the way, not just incidents in which the automated vehicle is involved, but incidents that the automated vehicle passes by. Because the best source of data about a crash between two conventional vehicles might come from the automated vehicle that was driving by right as it happened. And then finally, data that are incidental, data that are acquired during operation of the system, but aren't necessarily exclusively valuable for the operation itself. So it gives some examples of that. But another way of looking at that is, what data are collected about the vehicle itself, what data are collected about what's happening inside the vehicle, and what data are collected about what's happening outside the vehicle. So first, I want to acknowledge that there are all kinds of unimaginable possibilities for data. Data is, like any form of new infrastructure, full of unintended consequences, good and bad. We can think of the canals across Northern Europe, the railroads across the US, or ARPANET that eventually became our internet and gave us our cat videos. All of these were infrastructure with an incredible unforeseen potential. For example, many of us use Street View based on images that can be years or even older. Imagine a real-time Street View where you pull up an address and you don't see what happened on a random day 3 summers ago. You see what's happening right now. Or imagine that these vehicles find that it's increasingly difficult to move along congested urban streets because pedestrians have high confidence that the vehicles will at least attempt to stop when they step out in front of them. I think that's actually kind of exciting, but imagine that the companies that are developing these systems don't like it. What do? Well, they'll be able to record the pedestrians. They'll be able to facially recognize them. They could go to a police department and say, hey, would you mail a ticket, provided that the legal infrastructure exists for that. Or they could do what airlines or platform companies do today and say, well, you impeded our vehicle, you did something we didn't like, you don't get to use our automated driving service, or you don't get to use our robotaxis, or you don't get to use all of the other services that we as a company provide. And in that way, effect a sort of automated enforcement by these private networks. These are examples that I include, good and bad, of the potential uses of these data that are incidental to the operation of the automated driving system. And this comes back to the set of questions we discussed at the break, which is the idea that it's not just that automated vehicles will be supercomputers. There'll be these mobile supercomputers powered by big batteries, fed by all the kinds of capable sensors I described inside and outside the vehicle, and then connected back to these huge companies with even greater collective computing resources. And so that is the set of data challenges and opportunities that automotive technologies present, regardless of whether they necessarily fall into these sub-baskets of assisted driving or automated driving or remote driving or connected driving. At some point, it's the technologies writ large that provide this tremendous power. So with that, Chelsea, I'll turn it over to you, and I think you will start your slides.
Yes, that is the plan. We'll see if I break it. Okay. All right, does everybody see my first slide?
Looks good.
Looks good. All right, great. So, that was such an awesome presentation, Brian. Thank you. The few slides that you had talking about the data flows, like the complex ecosystem, I think that's so great to talk about because it's not necessarily just like the manufacturer, the user. There's a lot going on in this space. And that's something that I want to continue talking about in this final presentation today. So this is an older infographic that FPF created a couple years ago. We've already talked about all of these different types of data that's collected, generated, shared, as well as the different use cases. And just what I want to do is not so much point to any policies or solutions, but more just kind of get us thinking about some of the implications. So a lot of what this will be thought experiment like. So when you think about all of this type of data, consider what's personal data, what's not personal data. Is there any privacy or other impact from other types of data that's about the vehicle or use of the vehicle, even when it's not personal data? Who is the data controller? Who's the processor? Who's the owner of the data? There could be many. Who has access to the data and who should have access? So these are only some of the policy questions that are raised, but without having the technical understanding of the data flows, it's really hard to answer these. So that's why I really appreciate Bryant coming on today to get us somewhere into this conversation. Understanding the data flows is also important for liability. There's one question in the chat about this. I'm not going to directly answer that. It's not the main purpose for today, but totally agree that that's a valid question, and understanding these data flows and all of the players in the ecosystem will help get there. Just trying to switch slide. There we go. Brian's again touched on these. So this is just a very high level, non-exhaustive snapshot of the regulatory landscape for cars in the US and Europe. So you see a lot of this is focused on safety. And the reason for that is because I'm finding a lot of the safety regulations are really driving the technologies. So you're seeing in the US, just last week, NISTA launched a new AV testing initiative. In the new House infrastructure package, there was a bill talking about crash avoidance technologies, being able to detect the presence of a person in the back seat. So this is getting at whether there's a child left in a hot car, and then driver monitoring tech. Same with Euro NCAP, the new car performance assessment standards. We're seeing a lot of push towards having driver monitoring technologies. So really, as we go towards automated driving, the driver monitoring systems will go hand in hand with that. So we're seeing that the legislation is setting a minimum standard, while these safety regulations like Euro NCAP is concerned with setting the best possible practice. So these regulations, the standards, they're setting the requirements, but they're not descriptive of what the technology that the companies have to use to meet that standard. So I think that's a really interesting point. So for example, with driver monitoring systems, companies with the driver assist technologies currently in use different ways to monitor the driver. And we touched on that earlier in the presentation, whether it's with camera sensors or just with the pressure on the wheel, the torque sensor, which can also be hacked. I don't know if you've seen any of the YouTube videos with people just putting an orange in the steering wheel. So whether that works or not. So when thinking about designing cars for safety and function, why not think about also designing cars with privacy and data protection in mind? Something that I'm very interested in. So we know that in the EU, data protection by design and by default is a legal requirement in the GDPR. And then over here, sorry, my slides are lagging a bit. Over here in North America, we refer to this more as privacy by design. So we have the 7 foundational principles that are actually from the Ontario Privacy Commissioner. And then over on the other side of the screen is an FTC report from 2012, and they also talk about privacy by design. So I want us to think about everything that we've discussed, learned today, and think about applying a privacy by design example to optical sensors with computer vision. So again, when we think about designing vehicles for safety and operation, could we also think about designing for privacy and equity? So for the thought experiment, imagine you're a privacy lawyer and you're working with designers and engineers on a new driver monitoring project. Based on everything that you've learned on how the technology works and the purposes, what are some ways that you could build in privacy and data protection by design? So I've come up with my own list. I'd love for folks to add yours in the chat. Some people actually have already raised some of the questions. So that's great that people are already thinking about this. And when you think about privacy by design, it's not just the design engineering part of it, it's also the business operational side. So really having privacy security by default, by design into the entire business practice. So as a privacy lawyer in this fictitious company, some things that I might think about are so the first thing you would ask is what data do you need and what technology will you use to get it? So you could check the market for companies that are developing the technologies that you want. Which companies do you want to support? When you're the lawyer in a discussion with the other lawyers at the company, you could think about, are they willing to change some of their privacy data concerns to be more privacy preserving? Next, you want to only collect the data that you need. So first, you need to know what you need, and you need to know what technology is the best to get that. And then you could think about putting in things like de-identification on device, or ways to safeguard the data that's collected as soon as possible after collection. And then of course, for the basic retention, you only collect what you need and only keep it for as long as that you need it. It's a really easy thing to say as a general retention policy. In practice, retention policies are quite tricky. There's no one size fits all option for that. But definitely something that you need to have really, really good conversations internally in your company to figure out what is that best retention period. And other things like local processing of data, is that possible? Is it possible to not transmit, share any data and just keep it on device, in this case, the car? Are you going to want to do a privacy impact assessment before the launch? And also think about the whole life cycle. So life cycle thinking is about the data. So that's where the retention comes in and the deletion, but also the life cycle of the hardware. And I think this is crucial when we're talking about like robots, sensors, anything that has that physical component that we're putting out into public spaces. Thinking about the life cycle of how long that's going to be there and what it might look like 5-10 years from now. And then finally, this came up in the chat, which is really cool. What assumptions are you making with the technology? So someone in the chat raised the assumption that they'll save congestion, different things like that. So what assumptions are we making with the technology and how are we backing it up? And with that, consider any of the unintended, unethical, or inequitable impacts by the use of the technology. So there's a lot of examples of this, but it could include making sure that the data is fit for purpose, that the technology won't impact certain groups of people in harmful or negative ways. And also think about whether just the presence of the technology at all will harm certain individuals or groups. So by saying all of this, obviously I'm including individuals, but also thinking about societal and group harms. I think that's really important, especially in this space, to think about that. And then finally, accountability and empowering people inside of the organization. So if you have product designers, engineers working on technology, are they able to raise red flags if they see something, or just to take questions? Are they being taken seriously? Are they able to raise this up to management if they see something that's going on? So these are all just kind of my thought experiment of coming up with different things that I might ask if I was a privacy lawyer looking at this specific example. But I would love to hear from other people in the chat if they have other experiences, questions, or thoughts on this, or really about anything in the presentation. So we're wrapping up.
Awesome, Chelsea. It looks like there are a couple of questions in the Q&A so far, some of which might be getting into sort of more policy questions that aren't the subject of this presentation, but I'll defer to you on that one.
Cool.
Um,
Moving around things on my screen to try to get the chat bubble, so I'm a little bit delayed.
no worries. And I think we're just going to go to video while we chat and while people think about it. And while you think about it, keep in mind we also have the possibility to unmute you if you're interested in speaking your question, with a reminder that the presentation is recorded, but you're also totally welcome to chime in that way if anyone would like to ask a question verbally.
Let's see. So I see there's a question. How do the needs of the insurance world link into the discussion? Third-party use, the insurance industry wants individual driving behavior and where you go to make policies for you and you alone. It's been interesting to see discussions about data ownership in vehicles. They've been, at least at the US state level, confined to this narrow sense of a event data recorder or black box that records a tiny fraction of potentially relevant vehicle data. Because there are federal standards for what this collects. Some states have passed legislation that specifies the vehicle owner owns those data. But those states haven't really thought about the broader consequences of data, the data that might be in systems other than the EDR or on off-board systems. Insurance companies have tended to favor those state laws that place ownership of those data in the vehicle owner, because then those insurance companies can, by contract, require the vehicle owner to make those data available to them. There will be a tremendous amount of data available in incidents involving automated vehicles, probably too much to really reasonably manage under our existing systems. And so that's one set of questions, sort of data after a crash. The other are the kind of data that insurance companies need to understand the risk of their insured, whether that's an individual owner, driver, or company. And that's something that I think actually the market can handle quite well, insofar as there are incentives in place for these data to be made available or obtained. Did that address the question about insurance?
Looks like we've got a follow up on that question.
Mm-hmm. Yeah. So what's the leading idea for attributing liability? And by that, I assume you mean civil liability. That is who pays for injuries. We can also talk about criminal liability, but that falls into concepts of culpability, where the answers are actually a little clearer cut. In terms of civil liability, it's first important to remember that multiple parties can be sued and held liable, right? So it could be that under a hypothetical situation, a sensor manufacturer has built a faulty sensor, a car manufacturer has failed to properly test it, they've overrepresented to a user hasn't properly supervised, and the dust hasn't been wiped off by the company in charge of maintaining. And so it's really a very fact-driven question. But on the broader question of really who is the driver, like what is the stand-in for the driver, there are several different concepts emerging. One is sort of an insistence that there remains a human driver, a human user, and they retain liability. Often this is a fiction because it's a way of reaching their insurance, reaching their insurer. And in fact, the UK has dispensed entirely with this fiction and made insurance companies directly liable for crashes involving these kinds of future insured vehicles. Another is to identify some entity that's an appropriate stand-in for this driver. And we'd like to say that that might simplistically be the manufacturer, but when you have these multiple companies involved, like one company sells the vehicle, the other installs the software, the other installs the hardware, the third maintains it, the fourth deploys it, it's harder to pinpoint what a manufacturer or what a company might be. So the model legislation, the Uniform Law Commission, proposes a concept called the automated driving provider, Australia and the UK have echoed that in the automated driving system entity. Some entity that is most closely associated with the operation of the vehicle that essentially steps into this role of driver, in part by raising their hand and saying, I'm going to be it. And then we've also seen some particularly in the US state laws that sort of eliminate this concept of driver in functional legal terms by calling the driver the system. Automated vehicles are not legal entities, they're not legal persons. So that leaves some uncertainty of what that actually means in legal practice. But those are, I think, the prevailing approaches for thinking through this notion of civil responsibility in a narrow sense, recognizing that any factual situation will be much messier and involve many more entities.
Right. So I think, well, we have one person in the chat with their hand raised, and they'll probably take us to the end of the hour. So Marta.
Yeah, I think so. Yeah, Marta, we are going to unmute you. There we go. You may also have to do it on your end. So I'll prompt you to do that. Marta, we've unlocked you on our side, but I think you have to also unmute yourself on your platform. There we go. Oh, and we're muted again. Okay. Technical difficulties there. Let's move on to our one last question in the Q&A.
I think it's a great commitment to privacy.
We literally can't unmute you for you. But you have one in the chat, Chelsea, if you want to take it.
Yeah, I'm just reading. Well, Brian, you kind of touched on this already, and I think you might be better suited to answer the question at the end.
Sure. So I'd make a kind of a key distinction here between the sensors and then the way that the data from the sensors are processed. LiDAR is one set of sensors, right? These are the light or laser equivalent of radar. And Tesla has very publicly suggested that LiDAR is not the path forward because of at least the current expense of the systems. And then I'd say the current expense of the systems and the lack of deployment on vehicles, as well as the fact that Tesla has vehicles on the road that do not use them and from which Tesla is learning. But there are lots of different sensors you can use to acquire information. So it's simply a dispute about which sensors are best. The second area that Tesla has differed from many of the companies is in whether all of these sensors, whatever they are used to build a detailed map in advance. And so a number of companies will take data, not just from LiDAR, but from camera and radar, and create this pre-existing world so that cars know what to expect. And Tesla has said that again, should not, and in their view, will not be necessary for automated driving, that their systems can rely on much more primitive maps of the kind that you and I use today. The third point then is the way that any of these data are actually processed. This is machine learning. And although there are certainly differences in the particular approaches that companies use, and there's some suggestion that we may need a new innovative approach, there's not really a disagreement. Everyone recognizes that machine learning is necessary, and that some form of neural network is the prevalent approach to machine learning at this point. And so I wouldn't contrast a neural network with LiDAR. I'd contrast LiDAR with other sensors, high definition maps with simple maps, and then various forms of machine learning with each other. Does that?
Awesome. So not seeing any other questions, I think we can wrap up just in the last few minutes. I just want to say thank you to everyone who joined us today remotely. and also let you know, of course, there will be one more session in the masterclass series that we've been conducting throughout the year. The next session will likely be in July or August, and we'll be talking about smart home technologies and end-to-end encryption in daily life, which of course is a growing topic of legislative concern, certainly here in the US. So we're really looking forward to that. And, you know, we tend to publish these things pretty broadly, but if you want to get absolutely, you know, the first notifications when we have time, date, and details, please join our listserv, which you can find again at fpf.org/classes. And you'll be the first one to be notified about that and get other details related to the masterclass series. I've also placed our email address and my own email address into the channel for any follow-up. Please feel free to reach out to us, to Chelsea, Professor Smith, with any other questions or any other follow-up that you'd like. So with that said, just thank you so much to our speakers. Thank you. Bryant, did you want to say?
Thank you. And when you do reach out, please call me Bryant.
Don't call him Professor Smith. Call him Bryant. Thank you so much, Bryant, Chelsea. That was excellent. We covered a lot of ground. And thank you to everyone for joining. And enjoy the rest of your day or evening.
Thanks, everybody.
Bye.